afternoon, at least West Coast time, good evening, the UK, and good morning, I guess, to others who may be joining us in other parts of the world. My name is Vint Cerf. I'm one of the members of the IPNSIG board, and it's my pleasure today to introduce Lara Suzuki, who's going to speak to us about the interplanetary internet and moving it in the direction of machine learning using DTN protocols as part of the underlying substrate. We're very proud of Lara at Google. She's got many titles, as you can see from this initial slide. She is responsible for most of our applications of machine learning for our customers in Europe and elsewhere. She's gotten very excited about the whole interplanetary internet idea, and she's bringing to it applications in machine learning. In addition to which, she's also put the ION implementation of the bundle protocols onto all three of the clouds at Google, at Microsoft, and at AWS. So she's got her fingers deep into many different aspects of interplanetary networking. Her biography is available to you. I recommend that you read it so that we don't take too much time away from her presentation. But I want you to know how excited we are to have this kind of talent working together with the other people in the IPNSIG pursuing utility from the bundle protocol system, which of course we hope will underlie the interplanetary network, which we hope will support the return to the moon, onto Mars, and to other parts of the solar system. So with that very unduly brief introduction, I'm going to turn this over to Lara to tell us what's happening in machine learning in the interplanetary network space. So Lara, the floor is yours.
Thank you. Good evening, everyone. Good evening because I'm in London and here is like 7 p.m. And I am Dr. Lara Suzuki. I am a computer scientist and engineer. And it's 7 p.m. here, as I said. So I have a support dog who wakes me up at 5 a.m. So forgive me if I stumble on my words. And as Vint said, I work at Google. And tonight I will be presenting to you my original work on DTN ML, what I call ML on top of DTN, and on using DTN ML using federated computation. That is the use of federated learning for us to learn from in a decentralized way. This work has been carried out by me under the supervision of Vint, Scott Burley, and Lee Torgerson, and some other friends of the IPNSIG. So there's a lot of materials to cover today, so I'll be running through them now. So the first thing we're going to address is like space communications. I'll very briefly address that and talk about my research agenda and outputs, and a short introduction to DTN ML and how that works on cloud computing. And then I'm going to present 3 demos that I'm going to run to you and talk about the future of work I'm doing, that is using federated computation for enable artificial intelligence to run on top of DTN. So as most of us might know, like communication with spacecraft in space is very different from communication on Earth. Transmission and reception episodes are individually configured, started and ended, typically by a command sent to the spacecraft. And extreme distances and signal interference makes communication between Earth and an interplanetary spacecraft a challenge. And the long distances involved cause significant propagation delays, even in near Earth space orbit. And some of the leading causes of such delays are satellites' constant orbital movement, the links handovers that we have from sending from one antenna to another one, the acquisition and loss of signal as satellites come in and out of visibility of ground antennas, and discontinuous vehicles operations as well. So this makes all very challenging and introduces a lot of delay in communication in space. And what we need for our next space missions of the future is a new internet spanning the entire solar system, in which we can connect spacecrafts with different devices and different satellites and bring that data back to Earth in a time that is appropriate, and using also artificial intelligence to benefit applications in space. So I have dedicated 20% of my work to conduct research in the use of DTN in cloud computing in order to take advantage of cloud services, scalability, reliability, and also advanced machine learning capabilities. I was part of the team who did the first connectivity of multi-clouds using DTN. I was the first to connect clouds with IoT devices and microcontrollers using multiple protocol implementations, such as MQTT, MicroDTN, and ION. I also worked on the first streaming of video using multicast over DTN on cloud computing, and also using Kubernetes engine to scale services, providing data to DTN services. And also the first to perform federated computation over DTN on multiple clouds. I have 17 GitHub repos available from DTN 101 to performing advanced machine learning on cloud computing. So I recommend you to check that out. And I have also built a collection of 15 functioning demos on a multi-cloud and multi-protocol environment, demonstrating the importance of interoperability amongst open standards. And what I'm going to be doing here today is talking to you about using DTN machine learning for anomaly detection in telemetry data. I will be talking to you also about image recognition, video intelligence, and also how we can use DTN via federated computation. So machine learning systems, they have recently started to be used in space applications to approximate complex representations of the real world. So if we think about space data, traditionally data processing and exploitation occurs through ground systems when satellites are overhead to download the data. That takes time, which we might not have, particularly with constellations that have hundreds of spacecraft data to process. And typically satellites collect large quantities of business and scientific data and downlink them to the ground where processing and analysis occur. In many cases, this is insufficient because downlink overload deriving from data volume requires relief, and the need for real-time information demands immediate processing. So not only disaster damage mitigation, but also telecommunications, docking operations, asteroid minings, and other autonomous satellites operation make use of this capacity. Using space-qualified signal processors capable of hosting powerful AI and machine learning applications, a spacecraft can become a data collector, exploiter, and disseminator, the brain of this nervous system. And that will enable satellites to deliver actionable intelligence directly to the person at the right time at the speed required. And we think that by enabling high-performance AI capability in small power-constrained satellites, we can get data processed on board by using artificial intelligence, which results in end users obtaining the real-time data that is tailored information for them, rather of data sets waiting to be processed. So this is the main idea of us to run applications on the edge and process the machine learning training and the heavy lifting on the cloud. So let's start from the first basics. This is how a typical machine learning model flow looks like. We take data, apply some magic, also known as machine learning, and on top of this, and then we get some valuable predictions. The key points to highlight here is that machine learning can be based on sensitive and very high volume of data. And ML is a black box that makes the predictions based on behavior of the input data. So if the behavior of the data changes, the outputs of the machine learning model is also going to change. And this machine learning model can be expanded into several steps of a workflow. And the challenge is much bigger in machine learning as the number and complexity of input columns increases. We hit a combinatorial explosion of things for us to worry about. So from left to right, for every one of your individual feature column in your data set, you have to do data preparation, look for missing values, outliers, high cardinality features, do feature engineering for each of those columns. You need to think about the right pre-processing to prepare the data for the following model that you are going to select in the architecture selection step. It could be multiple options per feature, to be honest. We have to do architecture selection, dozens of models you could choose from, including the more that come out of research community basically on a monthly basis. And for each model, you have to select the hyperparameters that are right. That could be potentially be a dozen of values set that you have to think about tuning, ensembling, and especially if you're trying to create a good model. So whenever you hit any snags, you basically have to restart. And this could happen dozens of times for harder data sets. And the entire process can take months, potentially dooming ML projects altogether as executive sponsors, they lose interest. So we have to do this rinse and repeat up to tens of dozens of times per use case. And to make the process of designing machine learning models more accessible, we have been exploring ways to automate the design of machine learning model. Among many algorithms we have studied, evolutionary algorithms and reinforcement learning algorithms have shown great promise, But here we will focus on reinforcement learning approach and the early results we have gotten so far. In our approach, we will call AutoML, a controller neural net can propose a child model architecture which can then be trained and evaluated for quality on a particular task. And that feedback is then used to inform the controller how to improve its proposals for the next round. And we repeat this process thousands of times, generating new architectures, testing them, and giving them that feedback to the controller to learn from. And eventually, this controller learned to assign high probability to areas of the architecture space that achieve better accuracy on a held-out validation set, and low probability to areas of architecture space that score poorly. So the one architecture on the left is a human build, and the one on the right is AutoML build. And then we can see how we can create more sophisticated architectures using this AutoML process. And when we think about our features extraction, as we work with deep learning and deep neural networks, we start getting more information as we extract from the various input layers of our neural network. So for instance, we can extract our edges, shapes, objects. We can detect whether something is a hot dog or not. We can use complex objects as well and identify them. And the classification part is where we have to work on. We just tweak that classification part, and then we can do what we call transfer learning. And the idea is when you have a machine learning model that can generalize so well in production, you can actually get that set of data and do transfer learning, which means that in the last layer of the neural network, you can put any input data, and then that model will generalize and will make the predictions based on that last layer of the neural network. But when we think about machine learning, we often think that is basically creating accurate, cutting-edge machine learning model. However, the reality is a bit different. We spend a couple of weeks on average solving for a machine learning problem, writing, for instance, our TensorFlow code, the months to productionize it. And that is what we have to realize, that when you create a machine learning model, you are just creating a fraction of the job. The true machine learning landscape looks much more like this. In order to really materialize the benefits of ML code beyond experimentation, we need to take into consideration other aspects of the machine learning lifecycle. For instance, data ingestion and validation, training and serving infrastructure, IT operations that are concerned with this general architecture, machine resource management as well. And this is well described in this paper called Hidden Technical Debt in Machine Learning Systems, published by the TensorFlow Extended team. So the idea that we have to have is now, how do we manage all this? How do we abstract from all this complexity and move away to a way that we can dedicate our time into our machine learning model and ensure that we have a no-ops platform that can run and benefit us on accelerating our time to market. And that is what I want to talk to you guys about, DTN ML architecture on Google and on hybrid clouds. So what cloud computing can offer is to very rapidly provide a radically simple to use intelligent data platform that provides actionable insights in real time to support data processing and machine learning engineering from space programs. I would like to highlight a few important capabilities here. So scalability and performance. So you can think about speed, scale, and adaptability. Cloud can enable exceptional digital experiences during peak time without sacrificing performance or reliability. In terms of science and exploration, cloud computing and DTN can increase science data return through interoperability and more efficient link utilization, can facilitate science across distributed platforms as well. So we can do the monitoring of a phenomena by multiple spacecrafts. We can deliver data from distributed instruments to a central processing node. We can communicate between the diverse space assets across heterogeneous links. And because DTN and cloud computing can also increase autonomy, it will reduce operational complexity, enable responsive mission operations, and also increasing in scalability. And because DTN and cloud computing decrease lifecycle cost, it enables reuse, increases interoperability, and facilitates streamlined operations and more efficient use of personnel. What we have seen in industry is there is a reduction in development time by 45%, and maintenance costs are decreased by 55%, and testing time 20%. That means that you can deploy new features and applications faster and reduce errors due to a serverless approach. And serverless approach is really a complete different way of doing data management and processing and analytics. So if you see this platform here where I say Google Cloud Platform, you can see we have many different services here, and they are all run on a no-ops platform. No-ops means that application developers will never have to speak to an operations professional again. And no-ops achieve this nirvana by using cloud infrastructure as a service to get the resource you need at the time you need them. So it's really a game-changing application. And on top of that, we can run our different systems and applications for mission optimization, for instance, for real-time data processing or anomaly detection as well, and use very different ISP that is individual software vendors. So we can plug that in an interoperable way using open APIs. And this is what I wanted to demonstrate to you guys here. I would like to take the concept of transfer learning in cloud computing to navigate you through what we can achieve with DTN ML presented in the work that I did here. So we took an architecture search capability similar to the one used for image classification and translation problems. We added a tree-based architecture to search space and automated feature engineering. And then we perform an auto feature selection based on importance and embeddings. So embedding is a relatively low dimensional space in which you can translate high dimensional vectors. So ideally, an embedding captures some of the semantics of the input data by placing semantically similar inputs close together in the embedding space. And this embedding can be learned and reused across models. We then use a bagging ensemble to get the best model as possible. Ensemble learning is a machine learning paradigm where multiple models, often called weak learners, are trained to solve the same problem, and they are combined to get better results. And the main hypothesis that we have is that when weak models are correctly combined, we can obtain more accurate and or more robust models. Very roughly, we can say that bagging technique will mainly focus at getting an ensemble model with less variance than its component. So that aims at producing an ensemble model that is more robust than individual models composing it. And after that task, we then make the predictions that we are expecting to do, either a classification algorithm, either like an image processing or a telemetry data. And in this slide, you can see a diagram of a partially no-ops multicasting hybrid cloud infrastructure. So we have different sensors here. So in Wokingham, we have this one using MQTT. So that is the AstroPi that we have. I also have like a smart plant detector. So I have my plant over here with some sensors plugged in it with an Arduino collecting data in real time about the humidity of my plant, of my rose flowers here. And then I also have video cameras also using BSSP and MQTT as well. And through a contact graph that we use in DTN, we then plug in the 3 different clouds. So I say partially no ops because only the Google Cloud part is the no ops, because Google is the only no ops platform available. And then we link that with the bundle protocol to talk to AWS and to talk to Azure. So we have those 4 different nodes that we have here on this image, one deployed in Madrid, one in Canberra, one in London, and one in Goldstone. And 3 of them is running ION, the DTN implementation of NASA. And we also run one in AWS with MicroDT3N. And so let me show you DTN ML in action. I call DTN ML DTN AI on top of DTN. So the first one is the anomaly detection in telemetry data. So as I showed you, I have this sensor here, like that captures like many different information, humidity, pressure, and we have the yaw, pitch, axis, and roll axis. And I collect that data in real time, and I stream that into the cloud using PubSub model. And I also have here my plant that I showed you, my rose plant here, that I have those sensors in it. So I have 2 wires placed in the soil pot to form a variable resistor, and whose resistance varies depending on the soil moisture. So this variable resistor is connected in a voltage divider configuration, and the Arduino that I have collects a voltage proportional to the resistance between the 2 wires, meaning that the more humid the soil is, the less voltage it will be measured by the Arduino. So I'm using a 1 mega ohm resistor and 2 wires so we can create this do-it-yourself soil moisture sensor. And the AstroPi is also used in the International Space Station. And here we can see an astronaut holding them, pointing to them in the ISS. So let's take a look into the architecture that we have for anomaly detection in telemetry data. So this is an end-to-end architecture. So from left to the right, we can see that we have many actuators, and then we have edge data collection control. Then we have an edge gateway in which we run TensorFlow Lite. And TensorFlow Lite is a light version of TensorFlow that we can do machine learning on the edge. Because sometimes the data, for the data to go to the cloud for you to do the machine learning is too long. And we need that to be faster. So we do the machine learning on the edge. And after that, we stream that data using Cloud IoT Core, using our PubSub. And we also store batch data in our BigQuery, that is our no-ops data warehouse. And after the data is ingested, we also configure updates in the devices so we can turn in and out the lights depending on anomaly detected. And we also use Vertex AI, that is our cloud AI. If you see at the right, we use Vertex AI and AutoML for us to identify anomaly detection in the telemetry data that we are collecting from those sensors. So I'm gonna open a notebook here to demonstrate how that works. Can you guys see my notebook? Okay, so I'm gonna run in real time. So, so we are gonna first import our dependencies here and customize how we are gonna present the results here. So this is, we have some configurations. By the way, this is called Jupyter Notebooks, that we can execute a code and see the code in a very interactive way. So I'm gonna initialize the variables that I have for my project, select the real-time data that I'm collecting from this plant that I have here and from my AstroPi. That is going to BigQuery, and I am going to do a selection of that data to retrieve this for us. And I'm going to split the data into train and test sets because we need to validate whether our model is working or not. And before doing the processing, I'm going to normalize the values of the data I'm collecting and represent my values in a feature layer to be consumed by a deep neural network. Then I build my deep neural network model and define the plotting curve, the plotting loss curve function, and the model and the plotting of the model function. So I'm going to see the accuracy and also the loss of my model. And then this is where I define the deep neural network model creation function. And I'm going to execute that one. And then we are going to call the functions to build and train a deep neural network. So I'm going to define a learning rate of 0.001. So it's a low learning rate, which ensures that we can achieve the gradient descent in a very efficient way. We're going to run 40 epochs and have a batch size of 10 times. So we're going to go 10 times over the data. And we are going to create that model. So we're going to train in real time here. So I am doing the epochs here. So if you see it's in real time running here, the epochs. So we see like the loss is decreasing and the accuracy is increasing. So for 98, it's going to 98.61 to 51. And what we see here is the loss curve. The loss curve that we have is this one that we have. So it's a good looking loss curve, but the accuracy is a little bit weird. So what we can do, we can tweak the number of epochs. So for instance, I can try to see maybe that is a particular case of overfitting. So I can run different epochs and again, run again and see what is going to be the accuracy of my model. So I see the loss is decreasing and the accuracy is increasing. So we can test how we can get the best model for us. So the accuracy increased a little bit here in the beginning, but it is still a little bit noisy. So the idea is for us to play with that information and identify what is the best model. And in here, I'm going to call a testing model. So this is what was the predicted output. I predicted it was an outlier, and the actual output was an outlier. Then I predicted an output 0, and the actual was 0. So I got it very well. And the output 1 here again, that was an anomaly in the data, I actually got it right. So you can see those metrics all running here using Jupyter Notebooks. The other example that I have is for us to use image labeling and object recognition. So I have my Raspberry Pi, and I have a camera, professional camera, HD camera, and I am taking photos of various objects. But for this example, I'm going to use some data from weather so that we can get some meaningful kind of value that is connected to what we are talking here. So the architecture works this way. We have TensorFlow Lite running on the edge. I'm running Kubernetes engine to give information to give images and locations for my camera to capture on. Then we ingest that data, and then we put that on image recognition AI running on Vertex AI that is in the right corner of my screen. So I'm gonna go back to Jupyter Notebooks, and then we're gonna run that together. So this is the image recognition one. So I'm gonna import my packages. I'm gonna import my variables. I'm gonna display the image. I'm gonna retrieve from my bucket the images that I need. So this is the image we are gonna be processing. I'm gonna extract the objects from the images now. So I want to see what that means. Is this a piece of land? What those other features in my image means. So we are gonna extract objects from those images and then show the results for label detection. So what I could find here, labels and confidence score, is that it detected 97% was water with confidence of 97%, tropical cyclone with 97% of accuracy. It saw clouds, 96% of accuracy, atmosphere, nature, a cyclone, an atmospheric phenomenon, an astronomical object. I have a funny image here. Let me see if I can do something. Let me see if I remember what is, let me see if that is number 2. That is me and my dog. Let's see if I can find that. No, it's not. I don't remember the name of the image. I was going to run an example with me and my dog, but that's fine. Let's go back and try to go to the next image, that next part, that is for us to talk about video labeling. So the idea is for us to process this video here. So this is a Lego robot that I built to mimic the Curiosity. So it runs around, and I took that video using a high-performance camera. And what I want to do is to process every single frame and identify what is in that frame. And for this, I have this architecture. It's a little bit similar to the one before, that we have TensorFlow Lite running on the edge. We have ingestion and the VM instance compute engine to collect the information, and I process that data in Cloud AI using Vertex AI. So this is the example that we are going to run. So let's go to the notebooks again. So I have this one here. So I'm going to import my variables here, import my project IDs. We are going to show the video for processing and annotation. So it's going to the storage client, going to my bucket and getting my my video. So it's supposed to show the video here for us. So yes, so this is the video we're going to be processing, and we are going to process every single frame of that video. So what I have to do is to instantiate what I call a video intelligence client, that I'm going to be extracting from each frame what it is that is seeing. So I want you to see the feature and also annotate each feature. So I'm going to run this again, this code here, that I'm initiating feature extraction, I'm initiating video annotation, and I'm processing video for label annotations. So after I'm done extracting those information, I'm going to go actually to the video and I will annotate it using the segment labels that I see on my video. So after this code is run, I'm going to show which segment that we identified in that and what is the confidence that we managed to achieve on each one of the frames that we detected. So let's see, come on, please work. So is it still running? When you see an asterisk here, it says that it's still running, capturing the video. Oh, it's stuck in here. So it's still waiting here. So let's wait. Let me try to run this again. Sorry, live demo is like this. So it's running this one. Let me reset the kernel just a second, and let's go up to the top and do my import again. Import my objects here, import my video from the cloud. I am going to instantiate feature and video annotation. So yeah, so now it's moving. So I'm processing video for label annotation. So what I'm doing here, you see the asterisks here is like I'm still processing the video for label annotation. So I'm looking for every single frame that I have on my video. So it finished processing now. Yay, great. Now it's working fine. And then I'm going to annotate each video segment with appropriate labels now. So what I'm going to do is to, oh, I put that one to execute again. Sorry, guys. So it's executing that back again. So let's wait for that to be finished processing. And then we can go and annotate the video segment with the appropriate labels. While that is processing on the background, what I'm going to do is just go back and talk to you guys about federated computing. And then we come back, oh, it detected, it finished, good. Okay, so what we have here is that we detected a toy with 98% of confidence. It was a Lego technique, which is quite impressive. We detected with the confidence of 37%. It detected it was a hobby and linked to art with a confidence of 60%. It detected it was a Lego with 88% of confidence. It detected it was a vehicle, it was a machine, and it was a robot. It says it was a robot, a technology, and a machine with 84% of confidence. So what we can see in this example is that we can use the power of cloud computing and DTN for us to process that data and distribute and multicast that information across different nodes that we have available. And that is the example that I had. Now, what I'm working now is what I call the DTN.
Yep. Lara, it's Vint. I'm going to interrupt for a second because there were questions in the chat that it would be good to answer before you go on to the federated learning.
Yes.
If I understood the questions correctly, people are wondering what is running in the Raspberry Pi and where is the BPV7 running? My impression is that you were using MQTT between the Raspberry Pi and the cloud resident BPV7 nodes. So we're not running the BP protocols between the Raspberry Pis, although there exist implementations of BPV7 on Raspberry Pi, but for this one, it was easier to do MQTT or DSSP.
Yes, and I also wanted to explore with different protocols to check interoperability, which is something that's why I did MQTT, BSSP, and MQTT again, and I also use micro DT3N on AWS. So for us to test like the interoperability of different protocols and different implementations of DTN.
Great. So thank you for clarification. We can go on now to the federated learning, if you like.
Okay, let me just jump to the slide that I need. Federated computation. Yes. Okay. So what I want to talk to you guys about why to learn on decentralized data to augment space ML through federated computation. So much of the data that we see is born decentralized. So billions of phones or IoT devices constantly generate data that can enable better products. It's easy to learn on data in a centralized place. However, centralizing learning introduces latency, intermittency, data caps, and battery life issues and privacy concerns as well. We can do all the machine learning training on device, but that limits the creation of newer experiences. So there's often too little data per customer, or maybe customers are not contributing too much to the machine learning model learning on their phones. So decentralized learning supports the machine learning in a collaborative way. So we have many extensions for decentralized learning. For instance, we have differential privacy, compression, and quantization. And the approach is generalized beyond model training. We can also do that using for model evaluation. So what I would like to introduce to you guys here is how to use federated computations to perform machine learning models on top of DTN. So we applied the ION implementation of the bundle protocol by NASA alongside a federated computation approach to train an anomaly detection algorithm for sensor telemetry data and image classification from the MNIST dataset. So our approach is catered where data is distributed across several devices in a highly uneven fashion, and where devices have significant higher latency, lower throughput connections, and are only intermittently available for training. So for instance, my spacecraft might be in and out of visibility because it's behind the other side of a planet. So we firstly initialize a global model in Google Cloud, which is then downloaded by the edge devices. Instead of requiring centralizing the training data in one server or in a data center close to the ground antenna, our approach enables edge devices, spacecrafts or rover to, first, collaboratively learn a shared prediction model while keeping all the training data on the edge, decoupling the ability to do machine learning from the need to real-time string heavily payloads to the ground antennas and be idle while waiting for a response back. So we are trying to also to decouple that ability to do the machine learning and not have to wait for when data is available. And in our model, edge devices improve their model by learning from data on its environment. And then they summarize the changes as a small focused update. Only this update to the model is sent to the cloud using encrypted communication. So where it is immediately combined with other edge devices updates to improve the shared model. So all data, again, remains on the edge device. So in a given round of federated computation training, between hundreds or thousands of, let's say, devices or spacecrafts, they will all download the same input model, do their own computation, and upload the results. So the coordinating server ends up with a stack of those shapes representing the results. Again, not the input data, it is the results of the machine learning models. And then we can use then techniques, for instance, federated averaging or some other techniques for us to combine those models. So this federated learning, in a nutshell, is many repeated rounds of machine learning orchestrated by a central server with different devices participating in different rounds. And at some point, the resulting model is good enough to go to the engineer who can then evaluate and put that in production. So one thing that is interesting is that the bandwidth and the latency limitation found in space communication motivated us to use federated averaging algorithm, which can train deep neural networks using 10 or 100 times less communication compared to a naive federated version of the stochastic gradient descent. So a naive federated version would be to get everyone and average everyone together and get the result. The key idea that we are using is to use powerful processors in modern devices to compute higher quality updates than simple gradient steps. Since it takes fewer iterations of high quality updates to produce a good model, training can use much less communication. And as upload speeds are typically much slower than download speeds, we are also using a technique that can reduce upload communication costs by another 100x by compressing those updates using random rotations and quantization. So we are carefully scheduling when training is run to ensure that training happens only when the device is idle, for instance, not doing science, and with available CPU and battery, so there's no impact on the device performance. And the approach outlined in this work enables the application of AI to aid space exploration while increasing space link efficiency, utilization, and robustness, and enabling more reliable and efficient data transmission, resulting in more usable bandwidth and the ability to do more science. So this is a work in progress that we are doing and exploring federated computations for doing AI in space. And this is pretty much what I wanted to introduce to you guys. And I would like to thank you very much for joining the session. And I'm open for questions that the audience might have.
Well, this is fantastic. You know, virtual applause. I don't know how you managed to get through all those slides as fast as you did. I would have lost money on that bet. Already, I have a couple of questions, and perhaps you can help me sort them out. The first thing is that if you're doing I guess you can take the slides away for now. That way we can see each other.
Let me stop the sharing. Yes.
There we go. So the first thing is that by running the actual learning at the edges of the net, you don't have to move all of the raw data back and forth, which is really a big help. Because either it takes a long time because of latency or it takes a long time because of data rate. But now let's suppose I have a trained model on, let's say I've got several rovers on Mars and they're locally training. If I wanted to share what they've learned, is there a way for me to export the model that each of these devices has learned to each other or to a central location? And I'm assuming, second, that the model is a very compressed version of all of the original data that trained the model in the first place.
Yes.
So now let me imagine for a moment that we collect the models that have been learned by these various rovers. And let's suppose, just for the sake of simplicity, we actually package that up and we send them to a central location on Earth, on a cloud where those models are now going to be somehow federated. So far, what I've said is consistent with what you've been saying, so I think. So now the question is, when I've landed back at the cloud and I've got all of these models from the different rovers, do all the rovers have to have exactly the same neural network configuration in order for me to combine their results and to export the results back to them so that they have all learned what they have together, what each has learned separately? I hope that's a coherent question.
Yes. what happens is when you are learning on the edge, we can do automatic model selection. So the architecture might vary amongst them. But the tensor, the way that we send the tensor is in a standardized way so that we can understand the tensor when it comes to for us to do the federated averaging algorithm. And what happens is from all those models learned from those architectures, we define and select the best one that works for all the rovers. And then they will have a uniform model. And then they will learn by themselves again, and the whole process starts. And it's not that all the rovers will be part of the same cohort. Sometimes if a rover has low battery or is doing science or something, we might not invite that rover to be part of the cohort. So we are going to have some differences in the architectures of the models running, but at some point in time, they will all be initialized with a model that they all share.
Okay, that's very helpful. The thing that excites me about all this is that it fits so naturally into a high latency environment, which is, of course, what we are expecting to experience, although local communications may be fairly rapid. And so we can imagine at least being able to do the training locally and in a low latency way. Let's see whether there are other questions that are in. Joel has one. He said, how easy is it to modify decentralized data while keeping all the copies up to date? I don't know whether that's a well-formed question, Joel, but let's see what Lara says about that. It's in the chat, Lara.
Yeah, I would need that to be a little bit elaborated so that I can understand a little bit better how to respond to that.
I'm not sure. Joel obviously has a model in his head about how this must be working, which is why he asked the question. My impression is that we're not trying to keep the training data in sync necessarily. What we're trying to do is to keep the models that have been derived from the training data in some kind of synchrony by combining them in this federated way. Samo has a question. I'm sorry, Joel, if we didn't answer your question, you might type in a new one to clarify. But Samo says, I'm wondering if we could use a machine learning capability on the edge nodes to help us with routing strategies in the DTN. Now, that's an interesting question.
Yes, I believe so. And I think that for those edge nodes, what we can also do using federated learning is prioritizing which data pieces they are delivered first than the others. So we can not only prioritize the data, but we can also identify using the contact graph, what is the best route for us to use and to pass on to relink that data until that data gets back to Earth. So that is one of the things that we can do with those edge devices, because they become an intelligent entity that is capable of do those learnings as well. That's why we have different types of TensorFlow. So we have the TensorFlow, we have the TensorFlow Lite and the Micro. Micro is for embedded devices. So if you see this Arduino here that I have on my plant, on my rose plant here, it's using the Micro, the TensorFlow Micro. So I put it in here and I get the humidity of the soil of my plant. So it's using the Micro, but on my Raspberry Pi, I use the TensorFlow Lite because the Raspberry Pi is more powerful than the Arduino that I have. So we can really do different machine learnings on different embedded devices.
You know what I find totally amazing here is that when you think about Raspberry Pi and Arduino, these are relatively inexpensive devices. But, you know, imagine doing this 20 years ago. You know, you have this mountain of computing equipment that would cost a fortune, would use up all this power. And now, you know, the cost and size and weight and power requirements keep dropping. And now we get to do this kind of science in your house at home.
Indeed. Now, yeah, we have Coral, also Coral with TPUs that we can do much more powerful machine learning on the edge. And that is really incredible. So there's tons of things that we can do, especially with the federated learning, which allows us to work on environments that are subjective to disruption, to delays, like the ones that we are discussing in space communication.
So this is fascinating. So David Terrazas asked the question, he says, what's the real-time resolution of the system? Like what validity can you expect from the machine learning system from how much time in the future. David, you must be asking about predictions here, because a lot of what Lara was doing was recognizing a state or a condition or an image, which doesn't have a time variant to it. Maybe would like to elaborate either in the chat or I don't know if we can turn your microphone on. Can we turn David's microphone on? If that doesn't work, maybe we can elaborate a little bit.
David, you should be able to talk.
Okay, so David Terrazas, do you want to say a little bit more about the time question that you have?
Sure. Can you hear me now?
Yes, we can.
Awesome. Yeah, so I'm curious about the real-time resolution, not from the prediction perspective, but like at the time of detection or like labeling. There is usually some milliseconds or seconds, depending.
Understood. Yes. So at the moment, I'm conducting an experiment for me to understand what are the minimum viable data size or image size that we can receive, that we are still capable of making a prediction. Because what we can do is like receive like data that is more compressed, for instance, smaller images and videos. And then because that will speed up the processing and also will create more throughput. So what I'm doing now at the moment is doing this experiment to identify under which circumstances we have more speed or more delay. So in terms of milliseconds, the results that I run here for you was using Jupyter notebooks on a Jupyter Lab instance, which wouldn't be a good indicator of time. But I'm doing those experiments to assess time, and I will report back into the community as soon as I have the results to report on the speed of processing.
Thank you for that. I hope, David, that explains what's going on here in terms of time resolution. Lara, it occurred to me as you were talking that there's another terrestrial example of where federated learning might be amazingly useful. Imagine that you have a bunch of self-driving cars and they are all driving in different parts of the city. I wonder if they can collectively learn things about the city and then share what they've learned in some way. You know, I'm not quite sure what that means, but to give you an example, suppose a car pulls up at an intersection and it figures out that the tree over in the corner is a tree and it's not going to cross the street. I'm just making this up, of course. Yeah. But it may be very important to report back to everybody else that there's a tree and it's not going to cross the street because it's a tree. So don't pull up and wait for it to do that. So yes. I wonder whether the self-driving car situation is ideal for the local machine learning and then the sharing of models.
Yes, I believe so. And I also think that, for instance, when we talk about like self-driving cars, we have to look for the assets that we have on the roads for identification of people, identification of trees and patterns in roads as well, and traffic lights. And one of the things that we can learn together is like, what is the velocity I have to be so that I can always get green light? And then we can share that with others. And you can share, for instance, when new for instance, in London, some time ago, we had a problem with drainage capacity. So we had a huge congestion in the city center. So what happened was that it was disrupted, it was really terrible. One of the things that we can do is to detect whether like some services is also being carried out in particular locations, and then use that to propagate the knowledge that that road is not available for use. So that is also a very interesting application for federated learning. And we use federated learning practice using the Google keyboard that helps us to predict much better what is the person going to type next, because we learn from people and then we can identify what is the best phrase that the person is going to compose. So the Google Gboard on our phones, on Pixel phones and other Android phones, they work using federated learning as well.
I can't help but imagine something that I know we do in the Waze application, the one that helps people, navigate. It will tell you, that there's a police car up on the right-hand side of the road a mile ahead. Eventually, maybe we'll be able to recognize that and then automatically report this to everybody else.
Indeed.
there is a question from Oscar. He says, how do you weight the data value to be sent to the machine learning system? Some data may be more important than others, and it might be interesting to determine which data to send first. How do we respond to that?
Well, one of the things that we do, I think you are talking about feature importance, because one of the things that we do in our architecture is to do feature engineering and feature selection, in which we find what are the features that contribute better to my model. Because there's this misconception that the more data, the better your model. It's not like this. If you have more noise than signal, you don't get a very good prediction in the end. So in the feature selection space is where we select what are the features that we're going to carry that will help us with the prediction. And that is the feature that will create the weights from our models. And those weights are the ones that are sent as a tensor to my centralized federated learning on the cloud to process the training data.
Yeah, I'm sorry, go ahead, Lara.
No, go ahead, Vint.
Well,
I was going to see if I answered.
I wanted to reinforce my increasing excitement about federated learning. Originally, I thought, well, it's nice to have because it seemed like a useful extension. But now I realize how incredibly important it's going to be for space exploration because of the serious delays and data rate limitations in the interplanetary backbone, even though we were hoping to move up into optical frequencies or wavelengths to increase data rate. It's still the ability to do the learning in a distributed fashion is incredibly useful for that application. So I'm really glad that you're adding that to the list of things we can do. I'm not seeing other questions, but Mike Snell, you've been monitoring. Did I miss anything? Okay, I'm not seeing anything. So
I'm sorry, I just couldn't find the unmute button. No, I think that you've pretty much caught it, and I agree that there's pretty fascinating terrestrial IoT application potential here also.
So let me, I think we can wrap up at this point, but I want to say two things. First, I want to thank Lara especially for doing this at night in the UK. We really appreciate your willingness to share this with us. It's an exciting prospect now to see an application of this kind that can be supported by DTN. The important thing I want to add to this is that we are hoping at IPNSIG to field a number of applications terrestrially to help us test the bundle protocols. And your work on the machine learning is a natural application for us to propagate. So everyone who is watching this either now or maybe later, please follow what's happening at IPNSIG. We'll be telling you about what our projects working group has planned for 2022. Hopefully we will have applications that people can download, kind of like SETI at home, only we'll call it Solar System Internet at Home, or SSI at home, to help us verify that our bundle protocol implementations and our edge applications are all working reliably. So Lara will be there with us, I know, coming up with new ideas. But in the meantime, again, thank you, Lara, for putting these new ideas in our heads in such a succinct and clear way. We really appreciate it. And
thank you so much for having me. It was really a pleasure to talk to you guys. Check my GitHub repo, because in there you can find all the DTN AI machine learning code there for you guys to use and to start using DTN yourselves. And yeah, again, thank you so much for having me. It was really a pleasure.
Thanks so much, Lara. And back to our host. Thank you again for streaming this and for recording this. As soon as the recordings are ready, I'm sure you'll send a note out to the IPNSIG distribution list.
Yeah, it'll go up on the website and the membership.
That's great. Thank you so much. Thank you, everyone. Have a safe holiday. Make sure that you save yourself from COVID, especially this new Omicron. It looks like a nasty customer. So we want all of you to survive so that you can help us make the solar system internet happen. So again, thank you, Lara. Now you can go have some dinner if you haven't done that already. And to the rest of you, happy holiday. Thanks for joining us. See you on the net.
Bye-bye.